Welcome to the latest video in your Design of Experiments course. Now this video is going to be a little bit longer, so maybe 50 minutes, so if you've got time, watch it. If not, I would put it aside to give it your full attention. This is one of the most important videos within the course if you want to become a practical experimenter using Design of Experiments properly. And what we're going to talk about today is the process of actually designing the experiment. So this is a very practical video. It's all about designing the practical activities that you're going to go through to pick the right experiment and to make sure that it's a success. So it's really important that you give this some attention. I can teach you all the theory in the world, but actually doing the experiment in real life is where you'll learn everything. This is where things will go well or go badly. Now I have a little template that I use in order to make sure that this element goes off successfully. You can see the template here. We're going to work through the template and fill it out in front of you so that you can see it. But one important thing before we start, I would spend one full day designing an experiment. Now the other crucial thing is if you're in a company, this is a machine and you're all interested in getting this right, I would spend one day with a team of experts. Now obviously if you're doing research, PhD, that type of thing, you might be the subject experts in the particular machine that you're looking at. That would be okay. Maybe you would spend one day, maybe to be less than one day if there's no discussion. But if there's a team of experts in the room, typically put aside one day. This is to make sure the experiment goes off exactly as planned. So let's take a look at the template and let's get into this video. Okay, so you can see the template here. Though there are two pages for this video. So you can see page 1 here. You can see page 2 here. And there's also an additional page, page 3. Now you've got this in your notes. So I've put this in your course. You can download this as the DOE template. So potentially 3 pages. So let's work our way through this. So this is to make sure this goes well. Now, even after 25 years of designing experiments, I still use this template. So let's go through it. Obviously, process. What machine are you working on? What is the system you're trying to understand? Straightforward enough. Problem statement. The problem statement is obviously what's wrong. So pretty straightforward. If you're in a manufacturing situation, maybe you might have some historical data as to how the current process works. Next one down, it says, what do you want to learn? Now I know what you want to learn. You want to learn how to fix this. You want to learn how to fix the problem. But actually the objective is, what do you really want to learn? I know you want to learn a solution, but maybe you want to do it cheaper. Maybe there's a sweet spot. So maybe what you've got is 3 or 4 targets to hit, 3 or 4 important performance criteria, and whilst maybe you can hit 2 or 3 of those 4 criteria, maybe you can't hit the 4th one and you're looking for the sweet spot. What else might you want? You might want to be robust to outside influence, outside variables. Maybe that's something you want to learn. Okay, so be detailed about this. What do you want to learn? This experiment is an opportunity to get the maximum information from the minimum amount of data. Then it says, what's the start date and the end date? In other words, how much time do you have? This would especially be important in manufacturing, where maybe you're going to do the experiment over a weekend, or maybe the manufacturing department has let you have the machine for a day. Of course, what you have to do is make sure that the experiment fits in a day. Typically, time is one of the areas that will make you compromise on your experiment. If you have a limited amount of time, then you're going to have to design the experiment accordingly. Next, what response do you have? What are you measuring? What are you interested in trying to optimize? Now, in my little table here, there is an area for 2 responses only. So we've just got A and B. If you've got more than 2 responses, that's fine. You know, if you've got 6 different tolerances you're trying to hit, write them all down. Typically though, on the response, there should always be more than 1 response. You know, obviously, whatever the problem you've got, that's one of your responses. But if nothing else, you could put speed, process speed as a response. You could put process cost as a response. So more than just a single tolerance that you're trying to hit, maybe we can hit the tolerance but go faster. Maybe we can have the same defect rate but go faster. So there's all sorts of knowledge that you might want to learn. Make sure you put more than 1 response. Then the next box says, what type of data have you got? Now then, the data must be measurable. The data must be measurable. So let's talk about this for a second. Okay, in a previous video, we gave you a sample size. The sample size, of course, is clustering around the 30 to 50 area. Now that sample size is based on the fact that you are measuring something. So we talk about that type of data being continuous. In other words, it's on a scale. We're measuring millimeters, we're measuring strength, we're measuring hardness, we're measuring volts, that type of thing. We're on a scale. If you measure pass and fail, a defect rate type of output, the sample size goes 1,000 to 3,000. So this is crucial. If you don't have a measurable output, invent a scale for it. So if you have pass fail, what would I do? I'd put the components on the table like this. Over on this end, maybe these are the good ones. These are the really bad ones. Over here, maybe this is just a pass, just a fail, and then I would give them, you know, maybe 5, 4, 3, 2, 1. I'd give them a score to generate a scale. You've got to have a scale in your response, otherwise the sample size and of course the cost goes Boosh! So measurable data is really important. Now the next box says, what's the anticipated range of the measurement? In other words, can you measure extremes? Now remember what you're going to do in the experiment. What you're going to do, of course, is create a design space. You're going to go high and low. So if this was 2 factors at 2 levels, you've got a design space. And what we want you to do is get the box nice and big to put a signal through the data. Obviously, if you do that, you bump the results into extremes. Now, if you've made a jig for manufacturing, of course, the jig for manufacturing just wants to measure within the little window where the tolerance is. But maybe you're going to make these results go outside that window. So will your measurement system measure the extremes? Check it. We want to make sure there's no errors in this experiment. It goes off perfectly. So check the extremes. Can you measure them? Okay, MSA results, of course. Now, we haven't talked about MSA on this course, but I would recommend that you look up measurement system analysis. That's what MSA stands for. Please make sure you do an MSA. If your measurement system is poor, your DOE is useless. Don't waste the DOE and then find out that you've got a measurement problem. Then at the bottom of this table, it gives us room, look, to select our variables, to select our factors. Now, I've only got room for 6 variables on this part of the table, but on the third sheet, there is room for lots of variables, so I added that in. So I don't want you to think that you are restricted to 6. I could only get 6 on that first page. Okay, so of course, what's the variable? What type of variable is it? So if it's measurable, like temperature, it's a variable measure. If it's attribute, like supplier 1 versus supplier 2, or material 1 versus material 2, then that is an attribute variable or an attribute factor. Is it controllable or is it noise? So if the temperature is temperature on the machine, that would be controllable. If the temperature we're talking about is the outside temperature, today's weather, well, that of course would not be controllable. It would be noise. And what that would drive us to think about is a robust type experiment. I will be talking about robust experiments later in the course. It's one of the bells and whistles that we add on to our experimental technique. But robustness is a special type of experiment when you have noise that you're trying to understand. Next, range of interest. Now, the range of interest here is probably one of the most important things on the whole table. Now, this is your high and your low choice. I mentioned earlier, you are going to spend a day with a team. Why will you spend a day with the team? Because they'll discuss the highs and the lows. This is where lots and lots of discussion could come up with your experts. They might decide that the highs and the lows are too wide. They might decide that the highs and the lows are too narrow. And there'll be a lot of discussion about this. Let me show you why this is important. Okay, so now what we're talking about, of course, is the size of the box. So we've got the high and the low value for each variable. You choose how big the box is. You choose where this box is in experimental space. This is important. These decisions are crucial to the experiment working really well. So let me show you what could happen. We're going to do a test. We're going to test at the low. We're going to test at the high. So we collect some data at the low. We collect some data at the high. And of course we're going to fill the gap with mathematics. So look at this thing. What we've done here is great because there is a nice big signal which is overcoming the small amount of variability or noise. So we can clearly observe the signal above the noise. That's fantastic. That's because of where we put the high and the low. But maybe we could have been more conservative than that. And we put them much tighter. And now we have noise, which is still just as big, but our signal, look, is tiny. Now the maths won't like this. So you will miss possible knowledge when knowledge was really available to you. So what do I want you to do? I want you to get this box out and I want you to be bold. Be bold. Test in new areas. Learn something new. Okay, so we want to be out nice and wide. However, important, you must of course make samples. If you go to a region where the process doesn't produce a measurable item, we don't want that. We want to be out learning stuff, but in order to learn stuff, we got to make pieces. So if you've turned the machine to a real wild setting, nothing comes out the machine. It's no good to us. Now, this is why you're going to spend a day doing this, because this conversation could take a long time with the experts. Maybe a technician gives you their maximum time, their maximum temperature, and their maximum pressure that they've ever had the machine on. But then you show them the DOE pattern and they say, yes, but I would never turn all three up all at the same time. Well, okay, we've got to turn all three up all at the same time. Where do you suggest we go? It could be that you might have to do a little bit of one factor experimental work to decide whether the extremes will work for you or not. That's why this takes some time. All of the tests have to work. So if it's 16 tests in your 4-factor DOE, all 16 rows have to produce data. They all have to work. So you want to make sure this is right before you start. Really important that you get that bit right. You can spend a couple of hours in this box alone. Okay, so let's move on to the next one. Okay, so do we think the response is 2-level or is it 3-level? Now the advice I'm going to give you here is that you always assume that it's linear. Okay, so the two choices are that the model is linear, it is a straight line. Of course, the alternative is that the response is creating a curve, it's quadratic in some way, and therefore you need the third point to pick up the curve. My advice is until you have evidence that it's 3-level, assume that it's linear. 3-level experiments are always much more complicated, they're longer, they're more difficult to do. We don't want to be stepping into that realm if we didn't have to do them. Start 2-level, get the evidence that it's 3-level. We won't waste the 2-level data. It will all get used. But if you go to 3-level straight away, could be more expensive when it didn't need to be. So the next question is L12, the anticipated interactions. Now the L12 is sensitive to too many interactions. It will light up like a Christmas tree if there are lots and lots of interactions in it. Now personally, I've never seen this happen in 25 years, but I do know that it's a risk. The L12 is a special test. It does pick up interactions, even though you don't see them graphically. The L12 is designed to show them up in the numbers. And therefore, if there's lots of interactions, it can cause a problem, but it's a problem I've never seen, but we just have to be aware that that risk is there. Then finally it says, how are we going to measure the variable? Now what this means is, how are we going to set the +1 and the -1 values? Now it could be that you have a simple dial, you've got temperature on the machine, and of course you're just going to dial it to 70, you're just going to dial it to 90. That's fantastic. But other variables might not be like that. You might currently have air pressure on the machine, and you literally just open the mains air pressure and there is no scale to tell you what the air pressure is. Obviously, before you do the experiment, you might have to fit that air pressure gauge to the back of the machine. So there might be some pre-work needed so that you can definitively go to the +1 setting, you can definitively go to the -1 setting. If you can't do that, the experiment is going to be compromised. So make sure. How do you measure this? Okay. Then on to the second page, it says determine the number of resources to be used. Now this is going to mean about 40 rejects. Most of the parts you make are going to be rejects. Assume that before you start. So it's going to cost you 40 pieces. Now unless you're making gold ingots, I would expect 40 pieces to be relatively cheap. A relatively cheap day at the office. Especially if you're about to make another 100,000 really badly. 40 pieces is a great investment. If you can't make the 40, what's the risk? Well, the risk is that you get missing signals in your analysis. In other words, there is knowledge in your system, but you never see the knowledge because you didn't collect enough data. What's the worst thing that could happen to you here? Possibly if you don't collect enough data, you have to go back and increase the sample size, but you wouldn't waste the previous data that you've collected. Okay. Then the next box, box number 7, which design types could you use? So are you going to screen? Are you going to model? Do you need to add robustness to your experiment? Is it a 2-level experiment or a 3-level experiment? So there's an awful lot of choice here. Obviously, we've got the computer-aided menu, but there is some choice. Write them down, which is the best for you, which is the next box, of course. Select the best design approach. Great question, very simple, maybe not simple to answer. Now the best design approach is comprised of course, on one end of the scale, knowledge. On the other end of the scale is cost and time. If the knowledge is valuable and important to you, you're not going to be so worried about the cost and the time. If the knowledge is not important, you've got to be asking the question, why are you doing the DOE? But if the knowledge isn't important, you're not going to want to put the cost and the time in there. So you need to decide. This is a business decision. It isn't a statistical decision necessarily. You've got to use your wisdom to decide What is it that you've designed the experiment to find out? And therefore, is it worth the cost and the time? Then box 9. Can all the runs be randomized? And which factors are most difficult to change? Now, we haven't talked about randomization up to this point, so let's talk about what randomization means and why you might want to do it, why you might not want to do it. So let's talk about randomization. Okay, so let's introduce to you what Fisher did to randomize his experiments. Remember that Fisher is growing crops in a field, all right? So what he did in order to speed the tests up was he took a field and he split it up into units like this. And so for one growing season, he didn't do one experiment, he did 40 or 50 experiments in one go. But what he didn't do was this. He didn't put treatment 1 all in the one corner of the field. Why not? Well, maybe the field isn't flat. So maybe this field is undulating. And this corner of the field is in the shade. It doesn't see a lot of sun because it just goes over the rise and it's northerly facing. Well, clearly this zone of the field will suffer from the north face. It's not suffering from the fact that treatment 1 isn't any good to create extra growth. But because treatment 1 is all in that one area, it gets affected by an external variable. So in order to prevent that, scientists, and Fisher invented this, use randomization. And so what they would do is they would put treatment 1 all over the field like that. Then they do treatment 2 like that. Then they do treatment 3. And it's random. Now, if you randomize, you neutralize potential external factors. Now, if you think your process has got some of that in it, it's complicated, maybe there's something moving around and you think it's going to compromise your experiment, randomize the experiment. The weakness is especially the first variable, where maybe 50%, so your first column is 50-50 like this. If you've got the temperature of the machine, so this is especially true when you have a machining center, a CNC machining center. The machine might start off at room temperature and finish off at 60 degrees. And during the experiment, it warmed up. If this noise variable, because that's what it is, it's not in the experiment, if this has an effect, it will swing that effect into the first column, and the first column gets a bonus from a random variable. That would skew our results. Therefore, we do what Fisher said and we randomize. Okay, so that's randomization. Personally, I don't randomize because I try and get these under control before I start. So I've done additional work on my machines long before I've done designed experiments. But if you haven't done that and you're worried about it, randomize the test is a good way to go. Okay, conduct the experiment and record the results. Best advice I can give you is to make sure that you be there. Be at the experiment. Don't give the experiment to a technician to run and then you miss all sorts of things that could influence your result. Okay, so make sure you do the test and you are present. Then take the results analyze the results, draw your conclusions, do a confirmation test. You have learned nothing until you confirm your model. So what you're going to do, of course, is design the experiment, run the experiment, get knowledge, then you are going to confirm the knowledge. What confirmation means is you set up a random setting in your experiment, you make a prediction of where the results should land, and as long as you land where you predicted, you've confirmed the experiment. If you can't do that with a model, the model is useless. Always remember that in science. Whenever a scientist turns up with a model, make sure he comes with a confirmation test. If you can't do the confirmation test, the model's wrong. Throw it in the bin and start again. And finally, assess the results, make your decisions. In other words, pick your best settings, whatever best settings are. Maybe document the results, write your knowledge into your ISO 9001 documents, etc. Whatever documenting the results looks like. And that would be a great procedure for designing and conducting an experiment. Okay, so there is the process. You spend one day designing the experiment with a team of people. The idea is that you've talked through all the details. An experiment is something unique. You're going to do some tests to your machine that the technician never uses, because you're going to wander into reject regions. Well, of course, the technician is never going to want to wander into those regions, so you've never done work in that area to any great extent before. You need to make sure that everything is going to work, that the measurement system is going to measure it, that you can actually set the settings to those values. Sorts of things that have happened to me in experiments. I ran an experiment where we had welding. We had gas in order to test. We had the current gas that we used, obviously an inert gas. And an expert gave us a little bottle of different gas. And he said, oh, try this. I think you might find the welder will work better with this new gas. So I have a huge tank outside of the current gas that we use. I have a tiny little tank of the test gas that we're going to try. So we're going to do gas A, gas B. What happened halfway through the experiment? Gas B, the little tank, I ran out of it. I'm like, damn, now my experiment is compromised. Because the whole experiment has to be completed for it to be a success. So those are the type of things we're trying to get you to think through, and we're trying to get you to avoid. I've also had points where I've got well into an experiment, we've put the settings in, and the product wouldn't come off the end of the machine. And again, I had to compromise the pattern. I had to make it non-orthogonal. We're trying to avoid that type of problem. Don't get me wrong, can you always avoid it? No. You can spend a day doing the design and you will still get these problems. But if you don't spend a day, don't expect your experiment to work very well. We're trying to make sure that we can set the settings, we get signals, we get product, we get knowledge. We're doing things we don't usually do. Think it through, use the template, and everything will go fantastic, and then you'll get great knowledge out of your experiments. Right, now what we're going to be doing, now that we've looked at how to set one up and how to design one, we're going to start looking at some exercises. So we've got a number of exercises planned so that you can practice, practice and practice again until you get really good at 2-level screening and 2-level modeling. See you in the next video.